Today we're going to be learning about something called the natural number, as well as a formula or a way for us to change the base of logs in case we want to work with a different base that might be a little bit easier for us to work with, like maybe base 10 doesn't work, but base 2 would have been nice. So we'll learn how we can change the base. We'll start off with this mathematical number e, commonly referred to as the natural number, and it's called that because it actually shows up in nature a lot, and that's where it came from. So kind of like how pi came from always recognizing that the ratio of the circumference to the diameter always ended up being this 3.14159 number. Some really smart people a long time ago kept finding this pattern occurring in nature, and they ultimately figured out that it comes from this little kind of crazy looking formula here. So if we take 1 plus 1 over n raised to the nth power, and then we let that n value get really, really large, which is essentially what this crazy notation from calculus is saying. It always approaches this number 2.718281828, and it kind of keeps going. And it's irrational, which means that it doesn't repeat itself ever and just keeps going. I just showed in the calculator here, so there's the equation, 1 plus 1 over n to the nth power, and I just did a little table just to kind of show you that as we get bigger and bigger and bigger, bigger than the calculator can handle, we are already starting to get this 2.7183 if we round it to that place. So you don't need to necessarily memorize that e is 2.718, blah, 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 but just know that it's kind of like pi and it has a number and that it occurs all the time. And so what we're going to start off with is learning how to graph both exponentials and logs when they have a base of e, and then we'll get into some properties that we can use with e, and then ultimately we'll do that change of base. All right, so let's jump into it. We're going to start off with the graph of y equals e to the x. So we've been learning that exponential functions can be written as a times b to the x, but we can also rewrite them in another form, a times e to the kx, where k is just some sort of constant. And remember that e is also a constant. It is 2.71, blah, 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 blah. So in this kind of new way, we can define exponentials that have this base of e always. So every exponential in the world can always be rewritten somehow, some way, to be written as e to a power instead of whatever its original base might have been. And there's lots of pros and cons to doing this. Some people prefer to always use base e out in like the real world. That's what like mathematicians might really be doing here. We'll stick primarily with using our a times b to the x, but we want to just be able to recognize and know how to work with it in case e is our base here. So we got our growth and decay functions going on up here. So since e is always 2.7, our base is always bigger than 1, which means by default it should be growing. If our k value is greater than 0, and we'll ignore a for a second, but if k is greater than 0, then we will continue to grow. If k is a fraction, then we end up decaying instead. Here's what the graph looks like. You'll notice that it's the same as our normal exponential. We still have our 0, 1 as our start point. And then when we do e to the first, and then e to the second, and e to the third, and e to the -1, and e to the -2. So it does everything just like you're expecting. It follows the same domain that exponentials have, the same default range with no transformations. We have that it is, in fact, continuous, right? So yes, it's continuous. It still has no symmetry. It is always increasing from x values of -infinity to infinity. It is never decreasing. And it still has a horizontal asymptote at y equals 0. And our end behavior is exactly the same as what it was. We're going to use this notation and not our limit notation that we could use if we really wanted to. And we get that. Now, if I ever ask you to graph something that has e as the base, you're going to graph a single point and the asymptote, and that's all, okay? So if I ever ask you to graph it, you're just going to graph the horizontal asymptote and the one point that's going to be nice, which is always going to be the point that makes the exponent equal 0, because then e to the 0 power will be 1 times a. We'll always get a nice number as long as a is a nice number, okay? So that's basically exponentials. Now, when we switch it to logs, we commonly refer to a log with a base of e as the natural log, right? E is the natural number, so if we use it as a base, then we call this the natural log. And we use it so much that we decided to give it its own abbreviation. So we've already talked about how if you have log with no base, that it is assumed that the base is 10. So what happens here is we use log base e so often that we just decided that if we write ln, that really means log base e. Okay, so if you see this ln, it's really log base e. It's sometimes pronounced as lawn, like you mow your lawn. You might hear that from people sometimes. So we have ln or we have lawn. Ln is more common nowadays, I think. Lawn was a older way of saying it, I think. So if you see this ln of x, it really means log base e of x. Okay, and since logs and exponentials are inverses, this is just kind of showing you the connection between what y equals log base e to the x or y equals ln x is if we wrote it as an exponential. When we look at its graph, it looks just like a log graph because it is a log graph. We have a nice point right there, and we have a vertical asymptote that you can't really see me highlighting, but it is there. Same idea as the exponential. If I ever ask you to graph one, you would graph this single point, 1, 0, or whatever it was when we had transformations, and the vertical asymptote, again, wherever that was based off of the transformations. So just like normal logs, we have that the domain is greater than 0 and its range is always all real numbers. This thing is continuous, but only on its domain, right? So only from 0 to infinity. It doesn't exist with negative numbers. It has no symmetry. It is increasing, again, always on its domain, which is from 0 to infinity. It is never decreasing. And yes, we have our asymptote, vertical asymptote at x equals 0. When we go to do our end behavior, this time we're going to have it start at 0 instead of negative infinity because the x values can't go anywhere close to negative infinity. And we're going down as we get close to the asymptote at 0, and we're going up as we go away. So it's basically the exact same thing as graphing exponentials and logs with any other base. It's just that this base is a little harder to find more than just a single number. So we would basically focus on figuring out that right there and go from there. All right, some properties of logs that I want us to be familiar with. So we've already talked about these in terms of general logs, but let me show you what these properties are. I'm going to hide what the equal sign is for a second, even though you've now already seen it and it's printed on your page that way. And I'm going to add in a question mark here so that you can kind of see when I rearrange this where that question mark goes. So first we have that the base of all of these things are e, right? ln1, ln e to the x, and then e raised to the ln x. All of those ln's are really log base e. So when I go to switch this into exponential form, because it's currently in log form, I would get e to what power equals 1. And we know that that power must be 0 because e to the 0 power will equal 1. So that's why ln of 1, just like log of 1, any log with any base of 1, always equals 0. This next one, we have ln of e, right? So ln is really log base e. So when I go to switch this to exponential, I'm going to have e, and then it's raised to what power? And that will equal this e right there. So when we switch forms, right, we have the base to the question mark equals the inside. So we have e to what power equals e. Well, that power has to be 1 because e to the first will equal 1. So anytime that we have a log of the same base, right, so we have log base b of b, it always equals 1. Same exact idea is going to happen here. We have that our base is really e raised to the question mark, and that's going to equal the e to the x. So what does our question mark have to equal? Our question mark has to equal x, because if I have e to a power equals e to a power, those powers have to equal each other. So this worked with all of our other logs. When we had log base b of b to the x power, it always is whatever that power is for the same reasons. Now, this one's a little bit trickier. This is already in exponential form because we have e raised to the ln x, and x is in the exponent. So I'm going to actually switch it into log form. So I read, I'll do it out fully here. So we have log base e from that e right there of our question mark, and then it equals the ln x. And remember that ln is log base e. So when we're looking at this, I have log base e of something equals log base e of x. So that something must be x. And so that's why this happens. And again, this works for all logs. If I have b raised to the log base b of x, it is always going to be whatever that inside of the log is. So you just want to be familiar with these so that you can just save yourself some time. For example, right here, we have these little example guys that I'm going to bust out here. So I have ln e to the fifth, that's just going to be 5. So that is using the third property up there, that ln e to the x will always equal x. So ln e to the 5 will always equal 5. Here what I want to do is first rewrite this. E to the second in the bottom is going to really be e to the negative 2, because remember negative exponents will bring us from the bottom to the top of a fraction, and now I have the same property again. So this is just going to equal negative 2, so I'm just using this property right here. E to the ln 4 is using the fourth property, that's just going to be 4. And last we have ln square root of e. What I can do is rewrite that square root as e to the 1/2 power, and now I'm using property 3 again. This is just going to equal 1/2. All right, so you should pause the video now and try these for your terms that you got going on right here. So we have ln 1, ln e to the negative 4, ln the cube root of e squared, and then e raised to the ln 2. So pause the video and do that. When you come back, I'll go over. Did you pause the video? What are you waiting for? All right, I'll go over them for you. Here we got ln 1. Well, that's just using the first property way up top that we have there. So that guy's just going to be 0. ln e to the negative 4 is going to be negative 4. That's using the third property. What I want to do here is rewrite this in exponent form instead of radical form. So this is going to be e to the 2/3. So that's just going to, oopsies, got to write the right number, is going to be 2/3. And then e raised to the ln 2, that's that fourth property, it's just going to be 2. So being familiar with those properties makes life really easy for you to evaluate these ones. Otherwise, you would have to turn the first 3 into exponential form, set them all equal to x and turn them into exponential form and solve for what x would need to equal. And for part D, you would have to actually put that into log form, which would be a little confusing because there's already a log in it. Right, so that is our talk about the natural number e. So we have our natural exponential and our natural log, ln. And now what we're going to focus on is how to change the base. So here we have base 10, base e, and then base anything we want. What we can do is take log base b of x and split it into anything we want. So if we have the inside is x, that's going to go on top, and our base is b, and that goes on bottom with whatever our new base is. So remember, log x is really log base 10 of x, and then we have log base 10 of b. And this will be true no matter what base we use. So we can do the same exact idea. So over here we have log base b of x, and I can use log base e of x divided by log base e of b, and that will equal the same thing. We'll show you how to do this in the calculator actually in 2 seconds so that you see that this actually works. And the last one is just saying, hey, you could pick any base you want. You want base 1,000,000, you could do that. As long as these two, that's the worst color to use. As long as these two things are the same base, and you basically do log of the inside divided by log of the old base, you can change it to whatever base you want to be, okay? So if I look at this guy here, log 8 of 4, I don't see any immediate way of doing this without turning it into exponential form, and that's a little tricky. So what I'm going to do is switch this and change the base. So I'm going to say, hey, log 4 and log 8. 4 and 8 both can be written as 2 to a power. So I'm actually going to choose to make 2 the new power. So if I do log 2 of 4 divided by log 2 of 8, then that's going to actually be the same thing as doing log 8 of 4. And now what we need to do is just think about, like, what is this log saying? So this first log, right, it's saying 2 to what power? This is the neatest handwriting you've ever seen, is 4. And we know that 2 to the second power is 4. The bottom one is saying 2 to what power is 8. and we know that 2 to the third power is 8. So log base 2 of 8 is equal to 3. And we got that log 8 of 4 is going to equal 2/3. Now, I'm going to jump back over to my calculator before we do part B, assuming my computer lets me. There we go. Let's get out of this menu. Oof, okay. So depending on how new your calculator is, when you hit the math button, it's faster to go up. You might have this thing here that says log base. If you're lucky enough to have this, you can actually pick whatever base you want to have. So I'm going to do log base 8 of 4, which is the one that we were just doing. And when I hit that, that gives me 2/3, right? You can turn it back into a fraction so that you can see 2/3. I just want to show you that if I had done log base e, which is right here, right? Here's our normal log 10. Here's our ln, log e. I can actually do ln of 4, close the parentheses, divided by ln of 8, and that is also going to give me 2/3. I can do log of 4, close the parentheses, divided by log of 8, and that's going to give me 2/3. I can do log any base I want as long as I follow this pattern of log of the inside divided by log of the old base. It will always work with no matter what new base we pick. So there you go. You now know how to do it in your calculator. If your calculator is old enough and it doesn't have log base, you can, number one, try to make a program that will do it for you, which I can help you with if you need, or you can just learn the change of base, which you need to know anyway, and you would just do what I did here. So if you had to do log 8 of 4, I would just do ln 4 divided by ln 8. All right, so now let's see when this is more useful for us. So we have log 4, 5, log 5 of 9, and log 3 of 4. None of those have the same base. So what we're going to do is just not pick a base yet. So we're just going to say log 5 over log 4. So we're officially picking a base of 10 by not writing one, but we're just kind of leaving our options open to say like, hey, maybe I want to pick, log e, but I don't know it yet. So I'm just going to change all of them so they're all log 10. And since this is all multiplication, something kind of neat happens. I have a log 5 on top and bottom, and I have a log 4 on top and bottom. And what I'm left with is a log 9 divided by a log 3. Okay, so when I'm looking at that, 9 and 3, well, both of those could be rewritten as a base of 3. So what if I had picked 3 as my base all along? It wouldn't affect any of the things I've canceled, but now when I'm looking at this, I can say, hey, this guy's saying log 3 is 9. 3 to what power is 9? Well, I know that 3 to the second power is 9. And this bottom one, log 3 of 3, that always equals 1. So we have that this entire expression, log 4 of 5 times log 5 of 9 times log 3 of 4, is actually just equal to 2. Fun. Your turn. Do math. Try number 4 and see if you can figure that one out. Did you do it? Did I wait long enough for you to pause the video and try it yourself? No, you didn't even try it? All right, fine. You're a bum. You should try it, though, really, for realsies. Do it. No? Okay. All right, log 9 of 27. So 9 and 27 do not have, I can't raise 9 to a power and get 27 easily. I totally can, but not right away. But they both have 3 as a nice base, right? 3 squared is 9, and 3 to the third is 27. So I'm going to change the base to 3 and do log 3 of 27, so log of the inside, divided by log of the old base. And now I can just evaluate this kind of top and bottom. So log 3 of 27, that's saying 3 to what power is 27? And 3 to the third power is 27. And the bottom one is saying 3 to what power is 9? And we know that 3 to the second power is 9. And so we get that log 9 of 27 will equal 3 over 2. When we're doing this guy over here, we'll do the same exact idea. I'm going to do log 3 over log 2 times log 4 over log 3. So I'm just applying the change of base formula, and I'm not picking a new base yet because I'm not sure which one will work until I've kind of weeded out all this junk. So when I'm looking at all this stuff, everything just canceled. Wow. All right, so that entire log actually just equals 1. Pretty crazy. All right, last thing we got is evaluating these on the calculator. So we have Log 4, I'm just going to do all of these ones over here for us. So log is right down here, 4th from the bottom. Log 4, remember that it's base 10 if they don't tell us. So we're going to round to 3 decimal places. So we're going to say 0.602. Next one is ln. So ln is right below the log, ln right here. And we're going to do 17.4. So 17.4. And we get some crazy decimal. We're going to go 3 decimal places. So 2.856. Okay. Next, we have log 2 of 3. So if you have a fancy new calculator, you just hit the math button and you go to this letter A that says log base. And then we're going to do 2 and then move the cursor over to 3 and we hit enter, round to 3 decimal places. So 1.585. Okay, if you have an older calculator, you have to do the change of base. So we would do log 3 divided by log 2. Make sure you close that parentheses on that top one. We get the same number. You could also have done it with ln3, close parentheses, divided by ln2. Now you have to use the same base, so I can't use like ln3 divided by log 2. It has to be the same, but I get the same answer no matter what. The last one, we're not going to be able to do, right? Because log of any negative number is going to throw an error because you are not allowed to have logs of negative numbers. Okay, so it doesn't matter what our base is, that last one is going to not work. All right. I hope this video was clear for you. You have some practice that you can do right here. Not a whole lot of it, so good luck, and I'll catch you later. Don't forget to like and subscribe. Bye.